All right. So why is solubility part of this? Because solubility is really all about equilibrium. Camera go. All right. So this is exactly what you just did. And if you take a slightly soluble, now we're not talking about things with sodium and potassium, but when we take something that's slightly soluble, we have a solid that forms, right? And if we reach past saturation, we have a solid and it's turning into its ions. So we have that, again, that reversible reaction turning into ions, and the ions are reforming into the solid, and we reach what we call that physical equilibrium, right? The rate of solids turning into ions is equal to the rate of ions turning back into solids. When that happens, right at that point, that's when we've reached saturation. And then if you keep adding more, that molarity isn't going to change, right? You're just going to dump more stuff in and you're going to add more solid, and it's just going to stay solid, right? It's not going to go into solution past saturation. Yeah, hopefully you got that out of the simulation. My camera keeps going down. Oops, now I did it. Cool. All right. So when we talk about solubility, we can write an equilibrium constant for that expression. We kind of did that at the beginning, but we know K sub C is products over reactants. If we're talking about solubility, then what we're really saying is, since there are really no reactants or products, we write it like this, right? KSP is the concentration of the quote unquote products, which in this case are the ions that came out into solution, over the concentration of the reactant, but the reactant's a solid. So really there's just over one. So we do the same thing. We take the coefficients, we put them in as exponents, and that's what we call our KSP. SP, as I mentioned earlier, stands for solubility product. Notice, and this is not immediately visible, that in this case, the concentration, square brackets, concentration of the bromine ions is going to be twice as much. When you dissolve 1 unit of this, you get twice as many bromine ions. So the concentration of bromine ions in here is going to be twice as much. And if you actually looked and counted, there's twice as many of the bromine ions as there are of the mercury ions. Whichever one's mercury, whichever one's bromine. So keep in mind, because we're going to do some math where these concentrations matter as well as the exponents. All right. So what is molar solubility? That's the first thing we have to think about. Molar solubility is how many moles can we dissolve into 1 liter of water until we get to saturation, at saturation. Okay? So we know what solubility, we know what molarity is. And really it's just a molarity, but we're saying what's the molarity when we hit saturation? Once we, and if we keep shaking more stuff in here, that molarity stays. That molarity doesn't change because we don't have any more ions in solution. So kind of what's the maximum molarity we're going to hit if we dump a bunch of stuff in, it gets saturated, and that's it. That's the molarity at saturation. Okay. It's going to be confusing because we're going to use molar solubility to calculate something else and go back and forth. So make sure you understand the definition of molar solubility. So we've got that. We've got the KSP. We've got molar solubility. And let's think about what's happening here. So we're going to kind of take this apart. We've got this equilibrium. Barium sulfate, solid, reversible process, turns it into its ions. In this case, it's a 1-to-1 ratio of ions. And we reach saturation. Again, this did not dissolve completely. This is what we call slightly soluble. And we can represent the solubility in a lot of different ways. We can say, how many grams per liter can we dissolve in this? And if you look it up on the internet, it won't necessarily say moles. It'll say you can dissolve 0.2 grams of barium sulfate per liter, or 0.02 or point whatever. So that's kind of useful information. Sometimes they give it to you in grams per 100 milliliters. Sometimes, and this is what we're interested in, it's moles per liter. So you really got to pay attention to the units. Are we talking about grams? Are we talking about moles? Are we talking about liters or 100 milliliters? So the units are just as important as they were in unit 6. All right, so we're going to talk about moles per liter or molar solubility. All right, whoops. All right, so go ahead and write the K for this process. What's the K? The KSP. How would I write that? Corey, how do I write the KSP?
The concentration of PA times the concentration of ethylene.
Good. Yeah. So we're just saying, all right, that's our products, right? And we're just writing the expression. And again, that would be over the concentration of this, but this is a solid. So that's one. So that's the KSP expression for that. Now, SP again, solubility product. Go over my slide there. Good. All right. Now, where does the molar solubility come in? What do the square brackets mean? What are square brackets? Concentration. And these concentrations are the molar solubility. These are the concentrations at equilibrium, at solubility. I'm sorry, at saturation. Okay. So we know that square brackets are concentration, but we're going to focus more on what's the concentration at saturation. A lot of words. All right. So a couple things when you write these, remember it's products over reactants, which is kind of easy in this case. The coefficients, don't forget, if we had a coefficient of 2 or a 3, we would be cubing it or squaring it. And the concentration of the solid is 1. So I'm sure I'm going to see somebody try to get a concentration for solid. Don't be that person. All right. And KSP is unitless and temperature dependent. If we heat up the solution, we can dissolve more. So these concentrations, these molar solubilities change with temperature. Usually they're referenced at 25 degrees Celsius and 1 atmosphere of pressure, but we can change how much we dissolve in a liter of water. All right, let's get to some problems. So KSP, not the same as solubility. Some people are going to get that confused. They're connected. They're mathematically related to each other, and we're going to figure out how that works and how we can go back and forth. We need a balanced equation, and that's not really an equation. We need a balanced expression of solubility here, and then we're good. Then we can figure this out. We got to be able to write this. All right, so this is all right. Take another couple seconds, and we'll step through this because then we got to figure out, well, how are we going to? What are we trying to figure out? We're trying to figure out what's KSP. And all we know is how much of this compound can we dissolve in 500 milliliters of water. All right. Up here. How do we write the net ionic equation? What's the net ionic equation here? Hannah, what do you think is the net ionic equation? I'm starting out with the solid. I'm trying to dissolve it.
Into 1.
Okay. PB, what's the charge of PB in this case? Metals are always positive. Plus 2, right? Yeah. Chlorines. I got 2 negative ones for the chlorine, so this must be plus 2. And what else? 2 Cl minuses, right? Not Cl2. This is not diatomic chlorine. This is 2 separate chlorine ions that have been separated in solution. All right, what are we missing to make what? All right, yeah, these are in solution, so these are aqueous. What else am I missing? Yeah, this is going one way. This reaches equilibrium, which means this is a reversible reaction, right? This is once this reaches saturation, these ions are turning back into solid, which I hope you saw in the simulation. If you watch closely enough, you saw the ions reforming the solid. Good. All right. How do we write the KSP? Products over reactants, right? Alvin, what's the KSP? Square brackets, concentration?
Concentration of the PB plus Cl squared.
Plus?
Oh, sorry, it's like times the Cl squared.
Yeah, the pluses go on the ions, right? We don't add these together. We're multiplying these together. Cl minus squared. Good. That's our KSP expression. Again, it's over 1 because this is a solid. That's 1. Good. All right. So right there, you probably got 2 points. 1 for writing this correctly, and 1 for writing this correctly. Now, what are we trying to find? We're trying to calculate this. So what do we have to plug in here to calculate this? What? Hey, sorry for the interruption. Yeah, sure. What do I need to calculate here to calculate KSP? What are these square brackets? concentration at saturation. So we need to get the saturation concentrations here, the molar solubilities, another word for it, for these to plug in here so we can get to that. Make sure. All right. So how do we get these concentrations? What do we know about PbCl2? Let's draw a little picture. We put PbCl2 into water. What happens to it? It separates into Pb2 plus and Cl minus, Cl minus. How much of this can I dissolve? Well, it says 2 grams per 500 milliliters. So what's the molar solubility of lead 2 chloride? How do I figure that out? The molar solubility. Yeah, 2.0 grams of PbCl2. I got to turn it into moles because I want the molar solubility, not the gram solubility. 1 mole of PbCl2 is, what did I say? 278.10 grams. And that gives me the moles. And I want moles over liters. So what can I do to get moles over liters? I'm going to divide that by 0.5. 0.500 liters. And when you do the units, again, units are key. The grams are gone, and I'm going to be left with moles over liters. All right. So what's the molar solubility of lead 2 nitrate? Anybody disagree? 0.14? 0.14 or 0.01? 0.014. All right. So 0.014 units. Moles over liters or big M, right? So moles over liters. Good. Now, this is the molar solubility of this compound. What's the molar solubility of the lead ions? For every 1 mole of this that I put in water, how many moles of lead did I get? 1. So the molar solubility of the lead chloride is this. The molar solubility of the lead ions is this. Right? It's the same. For every 1 mole of lead chloride, I get 1 mole of lead ions. What's the molar solubility of the chlorine? For every 1 mole of lead chloride that I dissolve, I got 2 moles of chlorine. So at this saturation here, I actually have twice as much concentration of chlorine ions that I did lead ions. Yeah, that's important because if you miss that, everything goes wrong from there. And don't forget to square. All right, final question, a little bit of math. What's the KSP, the solubility product equilibrium constant for lead chloride, lead 2 chloride? Disagreements? Yeah.
I got 1 point.
It's 1.1.
That's not what I got.
All right, let's see. Did we square it? I got 1.097.
Yeah.
Yeah.
I think because those are rounded, so if you use if you calculated using the exact similarity.
Okay. Okay. Gotcha. So 1.1 times 10 to the minus 1, 2, 3, 4, 5. Minus 5?
Yeah.
Units? Unitless. Yeah, unitless. Just like every other K, this is a relationship between the concentration of the reactants and the concentration of the products. This is unitless. So this is not how much you can dissolve in water. This is a relationship between when it hits saturation, how much will be in solution and how much won't, right? What's the solubilities of these ions? All right, questions? These numbers, these KSPs will be small. You'll see some that are 10 to the minus 15 or 10 to the minus 20. Okay? Not directly, they're not a direct representation of this, but they do connect to the solubility of the ions. Questions on that? All right, we're going to go backwards too, but let's take a breather, take a breath here and see if there's anything we can. All right. All right. Let's see if we can go backwards. I'm going to let you guys do this. Yeah, I'm gonna erase this. I'm gonna let you guys see if you can go backwards. We start out with the exact same way we did it, right? We write a balanced net ionic equation. We write the KSP expression, and we know, in this case, we know what the KSP expression is. This is iodate, the iodate ion. You're going to need to use X, the letter X, or you could use the letter S for solubility. All right, I'm going to pause the video or the recording just because we're just going to be like cranking away for a minute here. So what do we know? We know that this is the KSP expression, and it's related to the molar solubility of these, which is what we're trying to find. We're trying to find the concentration in a saturated solution. So, in other words, what is concentration in a saturated solution is the molar solubility, right? That's another way of saying molar solubility, which is what these are. These are the molar solubilities at saturation. All right, so how would we solve this? Use a little math. All right, we know this is 1.40 times 10 to the minus 7. KSPs are small. What do we do in algebra if we don't know a number? X. Now, I'm going to use S because S for solubility. So you can use an X if you want to. I like using the letter S just for being different. So this is S. The molar solubility of copper 2 ions is S. What's the molar solubility of the iodate ions? 2S, because there's twice as many of them, right? So if we dissolve a mole of this, we're going to get 2 moles of this for every 1 mole of copper 2 ions. So now we have 2S squared. Not 2S squared, but 2S, parentheses, squared. All right, so now we solve. What do we do? What does that come out to? 4S cubed. 1.40 times 10 to the minus 7 equals what? 4x. Yeah, this is 4S squared times S is 4S cubed. I'm doing that with my 7th grader right now. We're doing stuff like this, so it's perfect. All right, now can we solve this with a calculator? Yes, hopefully. If you don't know how to find the cube root of something, we're probably going to be doing a slightly bigger roots than this, but not much bigger. What's that? Yeah, there's a button for it where you can put in whatever exponent or what do they call it? Not exponent. What's the opposite of exponent? Nth root. Nth root. Yes, you can plug in whatever nth root you want. All right. So what does S come into? What does S turn into, or X? Whatever. If you do this math,
0.0033.
0.0033.
Well, I mean, I'd probably round this. But I got 327.
Okay, let's call it 3.3. We don't want to get too many. Now, and this is notorious. It's very hard to nail down molar solubilities because the quantities are so small. What are the units of S? Don't say unitless. What are the units of S?
Yeah.
This is a molarity. This is M. This is how much. This is literally how many ions, how many moles of ions are in that solution. So this is the molar. So now what do we know about copper 2 ions? The concentration of the copper 2 ions is S, right? So the concentration of the copper 2 ions in saturation is 0.0033 M. And we could also figure out the concentration of the iodate ions if we wanted to. Didn't ask for them, but that would be twice as much. And these are not unitless. I'll say it again, not unitless. These are concentrations, moles per liter, or just big M. All right. Notice that this is not a lot of ions in solution. It's a very, very low molarity because this stuff here doesn't dissolve very much. You put some in a beaker and start stirring, it's going to sit at the bottom. Mostly. There'll be very little in solution. Yeah, Abigail. Okay. So yeah, let's take that a step back. We know that when we dissolve copper 2 iodate, we're going to get 1 mole of this and 2 moles of that. So again, I'll draw a picture. We dissolve copper iodate. This is key. I'm glad you're asking because If you don't get this, then everything just turns into X squared, and it's not always like that. We're going to have copper 2+ ions and iodate ions, 2 of them. So the concentration of iodate is twice as much as the concentration of the copper ions, because there's twice as many of them in the solution. And then the squared comes from the fact that when we wrote this, Ruth wrote this balanced expression, there's 2 of these, so that becomes the coefficient or the exponent for that. Yeah, so it's 2s parentheses squared, which ends up being 4s cubed. Yeah, so the important thing is you realize when you do dissolve, what little bit you do dissolve, there's twice as many iodate ions as there are copper ions in solution. Yeah, questions? Okay. All right. Not hard. Once you do a few more, you'll be good. Hang on a second. Right. All right, so it's all spelled out in the notes if you want to go back through. How do you get 3.27? Oh yeah, there it is. All right, so I'll tell you what, at this point we have 17 minutes. Most of us do. You can finish the simulation, or you can work on the practice problems that you picked up on the way in. Very similar to this. If you can do problems 1 and 2, solve them, you're good to go. You're exactly where we need to be. All right, perfect timing.
That's always so good. Like 20 I like demonstrating. I can find out kind of like